Yes, got it. We are recording. Okay, sorry about all that. I had to go in and change the due dates on the final exam practice problems. So those are gonna stay open until next Friday. And they're gonna close on next Friday. I haven't gotten a chance to look at them, but there are 25. The final exam itself is going to be 8 questions, free response. Like similar to the past tests, but definitely some of the new stuff we've covered since exam 3. Our final exam is, all right, so first part, to figure out when your final exam is, you Google UTSA Fall 2024 final exam schedule. And it takes you to, so click, that's what you Google. First link is a PDF, which I have preloaded. So our final exam is set for Friday from 11 to 12:50. I know for some people that is a craptastic time. It's one of the last ones. So I have found out that the class before ours, but not in here, in the room across the hall, which is actually bigger, they don't have a final at all because it's an AIS freshman, one of those classes. So I am stealing that room on Wednesday from 11 to 12:50. So that's why I have that one highlighted. I'm also giving an exam before ours at 9 a.m. across the hall. Then I have this one in here at 11 a.m., both of those on Friday. The only other one I'm doing is the 10 a.m. That'll be across the hall Monday from 11 to 12:50. So for people who don't want to take a final on Friday, like I can have a few people come to my Monday class, but like I can't just open it because then all of my pre-cal students will show up and then there will be no seats. But if you need to take the final on a different day, email me. We can figure that out. But the Wednesday for sure, like that room's just gonna be open. So if you want to take it on Wednesday instead and you're, you have that time free, feel free. Questions on that? Mhm. Friday at 11 o'clock. The one I have highlighted is the alternate time I'm going to host a final. But that'll be across the hall. It's 302.18. If I forget, somebody email me to remind me to post an announcement with the details. But I should be making that for my pre-cal classes too this afternoon. I just now assigned out the web work practice problems, so those are there. Can I do that on this one? Yeah. And there are, nope, wrong one. 25. Sorry, we're also doing practice problems for pre-cal, and those aren't fixed yet. And I have not added the bonus 10 points on exams 2 or 3 from web work. I'm gonna try to do that this afternoon. Like, it shouldn't take me too long. I just got to do it. I just had a whole lot of other things that shouldn't have taken me too long, and then they did. Okay, so we have class today. We're going to cover 5.3. Class on Wednesday. We're going to go through whichever of the questions on the review you guys want. I'll try to look through and see which ones I think look better than others. Better being a relative term. We do not have class on Friday. Friday is study day. So There are no scheduled classes on Friday, and instead all the departments schedule meetings. But that's your like extra day to study, because that one extra day is gonna help, we hope. Like I'm realizing reading other books, like in Britain, they get a whole extra week. And, you know, America being American and capitalist, we've just shaved that time down to a day. Yeah. Is what it is. So questions on any of that before we dive into 5.3? All right. So we have been learning a whole bunch of different things. Antiderivatives, and that the general antiderivative is the answer to the indefinite integral. And we learned a definite integral is the infinite sum of the rectangles, the area under the curve. So how the heck are we supposed to put all this together? So we have this function 3x squared minus 6x. And if we look at the area under the curve, where we start a at 0, and then we put it up to x. So up to a variable. So the kind of question is, well, what the heck would that look like? And I did have this loaded. Let's see if it'll load again. So right now our a is set to 0. And my x, when it's set to 0, our total area is 0. Now, as I move this over, you're going to see the total area number jumps around. So that point that's floating around is equal to the area from 0 to that number. So when we're in between 0 and 2, our area is negative. Sorry, I'm trying to move it slowly. And even a little past 2, the total area is still negative. It takes until I get to 3 that those two equal out. And now my overall total area is positive. So the idea here is all of these areas, like if I plot them on a curve, it makes its own curve. Oy. All right, so we see like on this side, because we're measuring backwards, it ends up being negative. But we get to 0 and it's 0. So we've got it's increasing, flattens out at 0, then it goes negative some more. We get to 3 and it's 0 again, and then it's increasing. So the shape of all of those areas is a cubic function. Like if I actually could convince Desmos to plot all the points, then this is what they're plotting. And if you remember our original function, 3x squared minus 6x, the antiderivative, add 1, divide by it, would be x cubed minus 3x squared. And then plus c for whatever generic constant. Since we're starting at 0, the c value is 0. So it's just to kind of show you the relationship between them, but that's all we got for the Desmos. Someday we'll be able to incorporate that better into the course. So if f is continuous over an interval, and we define a function, big F of x, to be the integral from a to x of little f of t dt. So they're separating what we're integrating with respect to versus the variable that we've put up here in the integral. So for our big function, the variable it's concerned with is this big X. The integral itself does stuff to functions, so we have it in terms of a secondary variable in here. But if I actually evaluate this, I'll be plugging in X, and then I'll be plugging in A. F of A will be some constant. So my antiderivative is my result from doing this. If I take the derivative of this ridiculous thing, I will get f of x. So f of x defined this way, big F of x, is the undo operation for a derivative. It is defined so that when we take the derivative, we get little f of x. So this is where a is some starting constant. If the bounds get different, we handle it a little bit differently, but overall, same idea. So here I have a ridiculous integral. All right, so I'm just restating what the fundamental theorem of calculus said on the previous slide. So if we have this kind of setup, this type of function, then we can figure out the derivative by just taking the function inside here and then plugging in x in place of the t. So we've got a couple of different notations here, and that can make this part look confusing. But here, our g of x is in the position of our big f of x from a theorem. So when they're asking for g prime of x, that's our big f prime of x. So that means the answer to this is, well, I'm just going to take my function form inside the derivative and just put my x in any derivative place and call it good. So g prime of x is -5, but instead of t cubed, we write x cubed minus 9. Yeah. So there is a way to do the antiderivative of this, and we would get some formula minus some formula with 10 plugged in. And then we would take the derivative, and the derivative would take us back to this formula, and then minus the thing with 10 plugged in is all a number, so the derivative of the number part would be 0. So we're coming up with our answer without having to know what the antiderivative of that mess is. Because me looking at it is not pretty. Is really not pretty. I think this would be a really ugly partial fraction decomposition. Cal 2 is where you're going to learn how to look at integrals and kind of figure out how to find those wacky antiderivatives. But if all it's really asking for is you need to do something with the derivative, we can just kind of take the integral antiderivative out of the mix. So now the bounds are a little screwy. So as long as the bottom starts with a number, we really don't care what the number is because the derivative will just make that part go away. But now instead of this being an x, it's some function in terms of x. So we're still going to do the derivative of this the same way. We're going to keep our same function, which is the big square root of 1 minus thing squared. But then we're going to have to multiply by the derivative of thing. And thing here is our sine of x. All right, so 1 minus sine squared. Does that sound vaguely familiar from pre-cal? Fair. So one of the identities that comes up over and over again from trig is the Pythagorean identity, which comes from using the Pythagorean theorem on the unit circle, basically. So you remember sine gets associated with the opposite side, which is y. Cosine gets associated with the adjacent side, which is x. And so if I have both of those squared, it would equal the hypotenuse squared. The hypotenuse in the unit circle is always 1. 1 squared is 1. So if I move the sine squared over, I get 1 minus sine squared. So 1 minus sine squared is the same as cosine squared. And then the derivative of sine is cosine. But just for what is the derivative? Like just answering out the chain rule, derivative of sine is cosine. Like we could have left it as the square root of 1 minus sine squared x times cosine x. The rest of this is just gravy extra stuff. So the chain rule was because this was not just an x. Because the bound wasn't from 12 to x, it was from 12 to some weird function. So this showed up here, and then as the chain rule, we did times the derivative of it. Yep, from two different ways. So I'd say it's like pure coincidence, but this kind of crap happens with sine and cosine, like they just transform from one to the other at the drop of a hat.
Doesn't matter what the sine x squared is outside of it. It goes to the cos squared.
So the recognized shorthand, if I put the squared on the trig function, is to mean the whole sine of x squared, what I have written out with blue and pink. If I write this, this is assumed to be that. Now, granted, I occasionally have students who'll put the squared in the wrong spot, and if the rest of their work indicates they meant sine squared, not x squared, I'll just kind of like make a note that's like, you should have written this here, but I know what you meant.
Sine x squared outside of parentheses. It goes to the trig function, not x.
So when it's the whole thing being squared, we put it on the trig function to differentiate it from this one. So basically it's like this one is considered bad math because it's vague. But we got real tired of writing parentheses sine x close parentheses squared. So that's why the shorthand was decided on. Now the odds of you ever having to do this, slim to none. It's not impossible, it's just highly unlikely. All right. So now we know that although the definite integral represents the area under the curve, there is still a connection between the definite integral and the notion of an antiderivative. So this is, how can I make Cal 2 nicer? And here it is. So if I am looking at a continuous function over an interval a to b, and f is any antiderivative of little f, then the integral from a to b is take any antiderivative and then plug in b minus what you get from plugging in a. Now the bonus thought question here is, why doesn't it matter which antiderivative we choose? So our generic antiderivative had the plus c. So whichever one of these I pick, if I'm doing f of b plus c minus big F of A plus C, what's going to happen to the C's? They cancel. So this is why it doesn't matter which antiderivative we pick. So we will habitually pick the one where C is 0. So we just don't have to think about it. So here to the end of Cal 2 at least, when you see an integral with 2 bounds, you want to figure out antiderivative, then plug the bounds in. So the integral is just to tell you what's the area under the curve, starting from A and ending at B. And so here we got a 2-part problem. So the first one is just what's the generic antiderivative? The second part is, all right, now I'm giving you some numbers. What's the area under the curve from -2 to 2 of that same thing? So this is generally how we tackle definite integrals. We kind of ignore the bounds, just do the calculus, then go back and plug the numbers in. So this guy is a product. Now, I know some of us forgot on the test, but the derivative of a product requires a special rule. So the antiderivative of a product would also require some craziness that I don't want to think about it, and it's too early for us to talk about. So really, we don't want to do the integral of this as is. We want to multiply that out so we just have regular power, like antiderivatives using the power rule. So this is a FOIL, whichever way you like writing it out. So we'd have 11x squared minus x to the 4th minus 99 plus 9x squared. And we're just going to leave the dx out there. All right, we do have a few like terms. There is a negative x to the 4th. Then 11x squared plus 9x squared is now a plus 20x squared. And then minus 99. All right, so now I've got some constant multiples in there, powers in there, but I've got an integral and a dx outside there. So I'm gonna just, so the integral and the dx are like the open and closed parentheses. They both go together. They're just like the defining outside part that says, do the antiderivative of what's between us. So if I distribute the integral through, I also have to distribute the dx through. So I can rewrite this as the integral of negative x to the fourth dx plus the integral of 20x squared dx plus the integral of negative 99 dx. Now the constant multiples in front can be factored out of the integral. So this is now like negative 1 times the integral of x to the fourth dx plus 20 times the integral of x squared dx. And you don't have to write out all these steps if you've done antiderivatives like you've done calculus before. It's okay. I'm just wanting to make sure we're all on the same page for anyone who hasn't done it before. And then this will look a little weird, but the negative 99 can be thought of as a constant. So then I just have the integral of dx. All right, so now I just have integral of x to a power. So the negative 1 is going to carry through. But now the antiderivative of x to the fourth, antiderivative, so the numbers are not going down, they're going up. So we add 1 and divide by it. So this will be x to the fifth over 5 plus 20 times x to the third over 3 minus 99 times our dx here. If it helps, you can think of that as an x to the 0 power. So I'd add 1, that's x to the first divided by 1. So that'll be 99x. So it's kind of ugly, but that is our antiderivative. Here. Plus C if you want. There's our generic general antiderivative. So to evaluate it using the bounds that we have down here, so I figured out my antiderivative. So what we usually write looks like this. I'm going to write the antiderivative. Negative 1 x to the fifth over 5 plus 20 x to the third over 3 minus 99x. And you can write the plus C or you can ignore it since we're evaluating it. Usually we don't even bother writing the C anymore. But since this got posed as two separate questions, I'd want to see the C answering what is the integral. And then when you're evaluating it, you can drop the C. All right, so now my antiderivative, and then we take the bounds we had and we write them at the end with, usually it's not a bracket here. Usually what we write is actually just a bar. So a vertical line with the bounds that we're evaluating from and to. And now here, we just plug the numbers in. So negative 1 times 2 to the fifth over 5 plus 20 times 2 to the third over 3 minus 99 times 2 minus, and now we're going to write all that again with negative 2's. And this is where you want to be very comfortable with your calculator and it doing fractions, because nobody wants to do that bullshit by hand. actually at HEB yesterday and I bought a calculator because I'm tired of using my phone and my phone doesn't do fractions. So I spent a whole $12. There we go. Yeah. -1 times open 2 to the 5th divided by 5 plus 20 times 8 by 3 minus 99 times 2. So we don't have to do it this way. I'm just going to negative 2266 over 15 minus put negative sign and negative sign, put a negative sign. So for Cal 2, this is a like standard evaluating an integral. You're gonna get stupid fractions like this. Your job is not to figure out what the stupid fractions are by hand. Your job is to be able to write the thing up top, the antiderivative with the numbers plugged in correctly. So this is why I've been harping about being comfortable with your calculator. Because anytime it's just numbers, that should be okay, I typed that in the calculator, meh. That is not the new thing that I am burdened with. That is just the finishing the end of the problem part. So questions on how that worked? Nope, still trying to absorb all the insanity. So I will say when you get more comfortable, you will very often go from the orange line to the purple line. So because you can write anything times 1 and x to the 0 is 1. So when we're looking at antiderivatives, when we take the antiderivative of just a number, we just get that number with an x. So that's why I was saying you can think of it like an invisible x to the 0, because then the power rule applies to that. But some people just remember, oh, if it's a number now, it's going to get an x. But it's the same as, like, especially when you're still getting used to the process of doing antiderivatives, like, don't be afraid of saying, all right, if I did it back, the derivative of x to the 5th is 5x to the 4th. The 5 would cancel the divide by 5. -1 times x to the 4th. That's where I started. 3 comes down, cancels the 3, x squared, 20x squared. Derivative of -99 times x would just be the -99. I did that for quite a long time before I finally got comfortable enough to just be like, boom, there it is. And I'm having to stretch my brain back to remember how I thought about stuff. That's the hard part. It's like trying to explain to a kid how you add. Like you think it's the easiest thing. You're like, you just add. Like that's what you do. Why don't you understand? Just getting a kid to be able to count is actually a lot more work than you realize until you have one. Well, I'm not saying you guys have kids or should or not. That is a personal choice. That's why I usually say nieces, nephews, or neighbors' kids. Like you have to understand the order the numbers go in, the one-to-one correspondence with counting, and that the number you stop at the end is the size of the thing you counted. And coordinating all three of those takes years of practice. That's why kids don't start elementary school knowing how to add. We're just happy if they can say the numbers in the right order. But it's a weird thing if you've never thought about it. All right. So now we got the integral of 2 over the square root of x. And we're going to evaluate that from convenient numbers that happen to be square rootable. I'm going to be recording a video. All right, so we can rewrite this x to the negative 1/2 dx. So that's x to the 1/2, but it's in the denominator. When I move it to the numerator, it becomes negative. All right, now this is in a power rule antiderivative setup. So I can, even though it's a fraction, I can add 1 and divide by that result. So it'll look weird, but I can do it. So the 2 is just going to carry through into our result. And now it will be x to the negative 1/2 plus 1 divided by negative 1/2 plus 1. And then plus c technically. So negative 1/2 plus 1 is positive 1/2. And then dividing by 1/2 is the same as multiplying by the reciprocal. So this becomes 2x to the 1/2 times 2 over 1. So we get 4 square root of x plus c. Technically, each of the steps should have the plus c, but this is what happens when you're thinking and writing, and it's not picture perfect. And this is why most calc professors are like, meh, if you didn't write the plus c at every step. But you do want to have a thought at the end of finishing an antiderivative integral. Do I need to write the plus c? That's why we had one of the memes before Thanksgiving was, hits the plus c button. Sometimes his memes make more sense after the fact. All right, so now we are going to take our antiderivative and evaluate it from 16 to 81. So this is the same as doing 4 square root of x with our bounds. So this equals 4 times the square root of 81 minus 4 times square root of 16. So we have 4 times 9 minus 4 times 4. 36 minus 16 is 20. So I don't know how long WebWork will be accessible to y'all, but going in and practicing these kind of problems, like this is the kind of stuff you want to be comfortable in on day 1 in Cal 2. Like this is where they're going to start to cover it like it's new. They're going to cover it like it's a review because they need to get to use substitution right away. All right, so I'll go ahead and record videos for the other 2. Talk about that last one, last summary. Make sure to look at the WebWork, final exam practice problems. Let me stop.